All right, so to summarize what I've gone through so far, we've discovered that the thing that the lock-in amplifier measures is actually the so-called sampled average temperature at the lock-in frequency, which is the modulation frequency. And mathematically, that's given by a infinite series over this function we call delta t, that's evaluated at a whole bunch of different frequencies that are offset by each other by an amount 1 over delta, or 1 over the period between pulses, and with a phase factor that's on the end that depends on the time delay. So I showed that that function delta t could be written in terms of a simple looking integral that involved this thing g, which was the point response function, the p, which was the spatial, or at least the Hankel transform of the spatial profile of our pump beam, which was a Gaussian, and the Hankel transform of the spatial profile of the probe beam. That's our thing S, which is also a Gaussian. And I actually took a little bit of time in a separate video to show you what the exact expressions for that P0 and S0 were. And they're Gaussians that depend on the spot shape and the Hankel transform variable k, and that is involved in that integral. The only thing that I haven't explicitly shown you how to do yet is calculate this thing g of k and f. So this is the point response function of the system. So essentially what it represents is the temperature profile that would build up in response to a point source of heating that was sinusoidally varied in time. So it's essentially sinusoidal heating from a point source. What we need to do is know the temperature response on the surface of our sample from that, and then we need to turn that. So the thing that we need is not really the temperature response as a function of space and time. In order to use it in this integral as it appears here, I actually need its Hankel transform and its Fourier transform. And actually, I'll show you that it turns out to be easier to calculate the Hankel transform and Fourier transform than it would be to actually calculate the spatial and time variation. And so, in fact, some pretty smart people have discovered that not only is it easier to do that, but it doesn't turn out to be significantly harder to do that for an anisotropic system with an arbitrary number of layers, as long as they're sort of pancake style layers where the layers have flat interfaces in between. So what I'm going to do next is show you how to actually derive the point response function in Hankel and Fourier space for an arbitrary number of layers. And this will be following a paper. So I didn't obviously I didn't discover this algorithm. This was an algorithm that was originally, I think, described by Alan Feldman and was adopted in David Cahill's seminal paper on this.